Okay, great. So in the last video, I solved for the final velocity at the bottom of our incline. And like I promised, I'm going to solve for the omega. So omega is equal to v over r. So now that we have v, we can find omega by dividing by the radius, which we have as 7 point, oh, I'm sorry, wrong problem. This one, 20. It was 20 centimeters, so 0.2 meters. So when we do that, we get 41.85 radians per second. So those are our final velocities at the bottom of our, here of our incline. B, what is the ratio of translational to kinetic energy at the bottom? Okay, so translational to rotational. So here we go. Let's, so it's basically asking kinetic energy, translational, kinetic energy, rotational. So when we do that, we're essentially doing 1/2 mv squared versus 1/2 I omega squared. So let's apply what we did earlier, basically this whole thing, to this situation. So I get 1/2 mv squared, that's straightforward. This is going to be 1/2. And you know what? I think what I'll do is, if you know, I'll show you. So I is still 2/5 mr squared. And omega squared is going to be the same thing that I have up here, v squared over r squared, so that I can cancel out the r's. These cancel out. So then I get 1/2 mv squared over 1/5 mv squared, like that. So if you see, this is crossed out with that, 1/5 mv squared. Well, that's nice because basically these cancel and these cancel, so I get 1/2 divided by 1/5. And, well, let me do that. So 1/2, if you remember, is 0.5. 1/5 is 0.2. So I get a ratio of 2.5 between the kinetic and the translational. Or in other words, you can see that there is more influence from the translational than the rotational. So that is our final answer for that part. Okay, let's do our final problem, which is angular momentum. So here we go. We have a person that stands at the center of a rotating merry-go-round on a platform, and then the moment of inertia didn't show up. So I can tell you what that is right there. That's 920 kilograms meters squared. I don't know why it didn't show up. And then the angular velocity, that is 2 radians a second. Sorry, I don't know why that didn't show up. I think those are the only things. Okay, so we got to calculate the angular velocity when the person reaches the end and calculate the rotational kinetic energy of the system plus the platform before and after the person's walk. So we got quite a bit of information. So the before is the person stands at the center right here, like that. And here's our rotating platform. And then they quickly, I think, right, rapidly, and then they basically go to this case when they're right here. And we know that the platform has a radius of 3 meters, like that. And let's see, platform has that angular velocity, which we have. Okay, perfect. Okay, so this is the before and after. So here is our momentum before. the person has no, since the person's in the center right here, versus this, right? What we can do is we can write the initial angular momentum is equal to the final angular momentum. So in this case, it's just going to be I of the platform times omega, and then we're going to set that equal to, since the person's right in the center of rotation, it's not going to contribute to our moment of inertia. So then what we have is the following. When the person's out here, this is going to put more mass on our system. So we're going to have the moment of inertia of the person plus the platform times its final angular velocity, like that. So basically what happens is we're looking for this. What's the final right here? So we actually are given the platform like that, and we could treat the person pretty much like a particle at the end of this. So what it's going to look like is the 920 kilograms meters squared times the initial rotational, right, that was the 2, velocity, is going to equal to the moment of inertia of the person. So if we treat them like a particle, then it's just going to be particle mr squared, like that. So m of the person is that. So 75. So 75 times r, which is the 3 squared, plus this thing is still on the platform, the 920, like this, and then times VF final, or omega final, like that. So I'm going to solve this now. Let's see if I got that. Where's my work? Yeah, perfect. Okay. So when I solve this out for VF or omega final, I get 1.15 radians per second as our final right there. Okay. Then it says calculate the rotational kinetic energy of the system of the platform plus person before and after that person's walk. So that's going to be basically the kinetic energy of the platform. Well, the initial is just the platform, which is what I meant to say. So it's going to be 1/2 I omega squared, and this is the initial case. So then I get 1/2 920 kilograms meters squared times the initial squared. So 1/2 920 times 2 squared gives me 1840 kilograms. I'm sorry, gives me joules. Like that. So that's our first answer. And then our second answer for the, it's going to be the platform plus person. So what we're going to get is 1/2 I platform plus I person omega final squared. So what this is basically I'm taking this scenario again and do 1/2 75 kilograms times the radius squared. That's for the person. The platform was the 920 times our omega, 1.15 radians a second squared, like that. So if we solve this out, we get 1054 joules, like that. So notice that this is platform plus person, after and before. You can see that we lost energy. That's because what happened is we slowed down right here due to the fact that we put more mass on the outside and it's harder to move this around. So that makes sense that we have lower energy right there. Okay, so that is the final problem. So we did a little bit of everything with rotation.